Lesson 3 is about the Pythagorean theorem and some other things about similar polygons and similar triangles. Triangles are polygons, right? Now the Pythagorean theorem, that should be familiar to you already. That deals with the relationship that exists between the sides of a right triangle. And let's say we call this side A, that side B, and this side C. Remember that side C, that has a special name. That's called the hypotenuse. In lesson 1 we talked about the fact that the angles and the sides opposite those angles of a triangle, they are related to each other. The bigger the angle, the larger the side opposite that angle will be. A 90-degree angle is the biggest angle in a right triangle. So that opposite side is the biggest side in the right triangle. It has that special name called the hypotenuse. Now, Pythagoras, he was the one who came up with this theorem. He didn't have algebra when he did it. He just related the sides. He said the square, or the area, the square area that would be created from side A and the square area from side B, if you add those two together, that would equal the square created using side C as the side for a square. And using algebra, that means that a squared plus b squared equals c squared. Basically what Pythagoras did was say that a square on this side that had a length of that side plus a square of this side was equal to the square that could be made using a side that was the length of the hypotenuse. Square A, I'll call that one. Square B, I'll call that one. Adding those two together would equal the area of square C. Now, some interesting things here about Pythagoras. Like we said in lesson 1, the Greeks, well, a lot of them anyway, not every single one of them, but a lot of them rejected God and made themselves God, worshipped nature, worshipped weird things. Pythagoras, he actually worshipped numbers. He lived around the 6th century BC, and his creed was this: "Bless us, divine number, thou who generatest gods and men." Kind of a strange guy. Came up with an interesting theorem, but you actually know more than Pythagoras did, so you're actually smarter than him. It doesn't take much to be smarter than somebody who worshipped numbers, who thought that the number 1 was the generator of all other numbers. God uses ungodly people all the time to get his will done. Here's an application of the Pythagorean theorem. Let's say you were building a roof for somebody, and the roof was going to have this triangular shape to it. It had to be 30 feet long to enclose the room that was below it, and you wanted that roof to come up 10 feet from there. You need to know how long to make this side of the roof. There's a great application of the Pythagorean theorem. What you would do, that whole base is 30, so you would just look at 1/2 of that, or 15 feet. That one tick mark there, that stands for feet. And so you would say x squared, which is the hypotenuse, is equal to 15 squared plus 10 squared, which would give you 225 plus 100, which would be 325. Do some algebra here. Take the square root of both sides there, and you would end up with x is equal to approximately 18.03 feet. So you've used the Pythagorean theorem there to determine the length of that side of the roof, and that would help you maybe know how much roofing material to get. So the Pythagorean theorem can be a very useful rule, and that might be a rule that you want to put down in your spiral notebook where you're keeping all of your definitions and formulas and rules in. Look at part B on triangle inequalities. Here's an application of the Pythagorean theorem just to determine what type of triangle you might be looking at. And if you had a right triangle, we know that c squared, or the hypotenuse, the longest side, squared is equal to a squared plus b squared. You could also have a relationship where c squared was less than a squared plus b squared. Think about it. Let's keep side b and, well, I guess we can't keep side b the same. Let's keep side a about the same length, and side b will make it a little bit less than 90. That means c would end up being a little bit less than it was in the first triangle. That's where c squared would be less than a squared plus b squared. That would be an acute triangle, right? Now, we keep a about the same length again. We could probably figure out when c squared would be greater than a squared plus b squared. That's when we'd have an obtuse triangle, when b would go out the other way. So what we're doing here, really, we are keeping a and b. I'm trying to keep those about the same length. We're just changing that angle right here, which makes c shorter in the middle triangle, made c longer in that last triangle there, in our obtuse triangle. So if you knew the lengths of the sides of a triangle, you could determine if it was a right triangle, an acute triangle, or an obtuse triangle by applying the Pythagorean theorem to it. So let's do a practice problem. Let's say that those three numbers are the lengths of the sides of a triangle. Figure out if that's going to be a right triangle, an acute triangle, or an obtuse triangle. Well, what you do there is you always use c as the longest side, so that'd be 10 squared, or just 100, and we're comparing that to 6 squared plus 7 squared, so that would be 36 plus 49. And so that means we're comparing 185. So look at that. 100 is greater than 85. That means c squared is greater than a squared plus b squared. Think about that. That means that we would have an obtuse triangle, right? So that would be what we would say for an answer. Obtuse. If c squared is greater than a squared plus b squared, that means that side is longer than it would be if it was a right triangle, so it must be obtuse. It's just another application of the Pythagorean theorem. Let's go on to part D. I'm skipping part C for right now because I think it's better to explain a similar triangle. First, we can use that to understand similar polygons. Let's calculate the height of a tree to understand how similar triangles work. And let's say we had this tree here. Not the best drawing in the world. I can do it a little bit better than that. Let's use that tree and let's see if we can figure out how tall it is. Well, what you could do, if you started right here and you knew what this distance was from here to the base of the tree, we could figure out how tall it was. Let's just go all the way up. Let's just kind of go up to the top there, and that would be even, pretty much even with the top. We can draw a triangle now back to that starting point, and we can assume that's a right triangle there. Now, like I said, if you knew that distance along the bottom, let's say that was 30 feet. The way you could figure out the height of this tree would be to have, let's say you had a friend that was exactly 6 feet tall. They could stand, you're down there at that point on the left, you're laying on the ground, you have your eye lined up with the top of the tree. And what you do is you have your friend walk until their head is in your line of sight with the top of the tree. The top of their head is in that line of sight with the top of the tree. They're 6 feet tall, so look at this now. And also you could figure out their distance from you. Let's say that was 11 feet. You've got similar triangles here. You have this small triangle, and the distance from you to your friend is 11 feet. The height of your friend is 6 feet, and we can assume your friend is standing straight up and down, so that's a right angle there. And then you have the big triangle up to the tree to the ground and back. That's 30 feet away from you. You don't know this height right here. Similar triangles are triangles whose angles are the same. If their angles are the same, that means their sides are proportional to each other. So we know that both of those triangles had this angle right here in common, and they both have right angles at their bases. So if two angles are in common, the third has to be in common as well, because the sum of them add up to 180. So that top angle, which I'll just put a red mark on, those are in common as well. We have all the angles are congruent, then that means the triangles are similar. Their sides are proportional to each other, and that means we can set up a proportion or a ratio, and we can figure out that unknown height. We can say 11 over 30 is equal to 6 over h. When you set up your proportion, it's always important to do each ratio in the same order. I went bottom left to bottom right. I wouldn't go top right to top left. I'd do each one, the left triangle to the right, ratio of left to right, or do both of them, the ratio of the right one to the left one. Now we can solve for h. 11 times h is equal to 180. Divide both sides by 11. H would equal about 16.4 feet. That's about how tall that tree is. We use that little single tick mark like that to represent units of feet, 16.4 feet. You might want to put that in your rule book about similar triangles. They have congruent angles and proportional sides. We can use that information to find missing lengths. Let's do a practice problem now. Look at practice problem C. You have two triangles there. I want you to find A, B, and C, side A, B, and C. So what you need to do here first is just see if you do have similar triangles, and the way you do that is to make sure they have congruent angles. They both have a 90-degree angle. These vertical angles have to be the same, so if they have two angles in common, then those third angles will also be in common, and I'll just put some green marks on those to designate them. What I like to do on problems like this is set up my proportions first, and all of those sides are proportional to each other, so that means a ratio, right? Ratios are equal fractions, and let's do the sides opposite the 90-degree angles first. That would be side A and C, so we would just say side A over side C. I always like to read them from left to right, and so now let's do the sides opposite the red angles or the vertical angles. That would be 4 over 8, and then we'll say the sides opposite the green angles, 6 over B. Okay, so we have those proportions there. Those are all equal to each other. We can come up with two equations from that information. A over C is equal to 4 over 8, and we can also say 4 over 8 is equal to 6 over B. Now that equation on the right, we can solve that for B. We just have one unknown. The equation on the left, though, we can't solve that one yet because we have two unknowns in it. We have to have one equation and one unknown. You can't solve an equation that has two unknowns in it. But look, we have right triangles, and look at the small right triangle. Can't we figure out what A is, the hypotenuse? Because we know what the other two sides are. So we can solve for A. A squared is equal to 4 squared, which would be 16, plus 6 squared, which would be 36. So A squared is equal to 52. Take the square root of both sides, and I won't write this in decimal form right now. I'll just say that A is equal to, well, that'd be 4 times 13. We could factor out the 4 and get 2 times the square root of 13. There's my answer for A. We can substitute that back into the proportion up there to solve for C. Let's go ahead and solve for B right now. We have that proportion over there on the right. 4B equals 48. Divide both sides by 4. You can probably just do that in your head. B equals 12. Now let's solve for C. 2 times the square root of 13 over C equals 4 over 8. Let's just simplify that to 1 over 2. And so we end up with C equals 4 times the square root of 13. And so there's our three answers. We could write them all together. B is equal to 12 and C equals 4 times the square root of 13. Put a box around all of them. We use similar triangles there. What we knew about similar triangles is that the sides opposite equal angles are proportional to each other. That's the fundamental rule when you're dealing with similar triangles. You can use that rule to find out new truths like we found out here. All of these rules that we're learning here, they're based on man's ideas. At some time, a man used inductive reasoning. In other words, he observed properties about triangles to come up with this rule that for similar triangles, when you have similar triangles, that means that all of their angles are the same and the sides opposite those angles are proportional to each other. Inductive reasoning was used to make the rule. Deductive reasoning is the application of the rule. Like what we did here, we applied that rule to find out a new truth about this triangle, that side A is equal to 2 times the square root of 13, B is 12, and C is 4 times the square root of 13. Now let's go back to part C on page 28 and talk about similar polygons. On those pages they have some different definitions of polygons, like what a concave, a convex, equilateral, equiangular, things like that are. Those would be good for you to be familiar with. I'm not going to really cover those right now though. Polygons, those are considered to be simple. That means their lines don't intersect. They're closed. Coplanar, that means they're all in one plane. Geometric figures whose sides are straight lines or line segments. Now, similar polygons, they have relationships like similar triangles. Their sides are proportional to each other. And a way we can understand this is to get a little artistic here. And there we have a square. We can do something called enlargement to understand similar polygons. Why don't you draw that square, or draw a square on your paper, and just draw a point, doesn't matter where, just draw it out to the outside, and then draw line segments that are starting at that point and they pass across, touch each edge of that square that you just drew. So like draw one out like that, then go to the top right corner, draw through that, then we'll go to the bottom right corner, draw right through the corner there, and then the bottom left one. Okay, now what you can do with that, you can draw another square anywhere on those lines that you just drew, and it will be proportional to that first one. The straighter your lines are, the better, of course. But as you can see there, we have a square, or pretty close to a square. I could draw a smaller one too. That would be also proportional to that original white square that we have drawn. Now, how are those proportional? Well, just think about it. Their sides all lie on a similar triangle, don't they? Watch this. I'll start with the big red triangle, go all the way down to the point, and then come back along the bottom. Now, can you see that triangle that's there? And this side that I'm drawing a tick mark through, this side right there and this side, they all are part of that triangle. And you could maybe just draw a side view of what I have there and see what I'm talking about a little bit better. So you have all three of those angles. Basically that bottom one is a right angle there, and then they all have this angle in common, so that means that all of those top angles they have in common as well. There's three triangles that you could draw there. All of them are similar. One of the most important applications of similar polygons and understanding how they can be similar just based on similar triangles is in map making. If you couldn't make similar polygons, you wouldn't be able to make scale models of different things, whether it's a map or maybe just like a model car that you were going to make. Every single drawing pretty much is a scale model of the real thing, whether it's a house or an F-16 or a Hummer. Just doesn't matter what it is. Somebody has made some scale model drawing of it to represent the real thing. Scale models, maps, they have proportional sides to them. Look at these two squares that I've drawn. All squares are actually similar or proportional to each other in some way or another, because all their angles are the same, right? They have the same number of sides, same angles. A side on square A has to be multiplied by 1.5 to equal the length of a side on B. 1.5 times A equals B. 1.5 is what's called a scale factor. This can work in the opposite way too. Side B, that is 2/3 of A. So 2/3 times B equals A. There's another scale factor, 2/3. A factor is something you multiply by something else, right? All the scale factor is another way of thinking of proportional sides, right? We could rearrange 2/3 B equals A, divide both sides by B, and you would get 2/3 is equal to A over B. The ratio of A to B is 2:3. And above, we could divide both sides by A, and we'd have the ratio of B to A is 1.5, which is the same thing as 3:2, right? Ratio of B to A is 3:2. The ratio of A to B is 2:3. That's all a scale factor is a proportion that you know the values of. So let's do one more problem. Look at practice problem D over on the right. I have two squares there. I want you to tell me what the area of B is, square B, if the scale factor is 1.8. Well, obviously square B is bigger than square A, so what we would have to do is multiply that given side of 10 inches by 1.8, and we get 18 inches. And then for the area, it's a square, so it would just be 18 squared, and that would equal 324 inches squared. Similar polygons are like similar triangles. Their sides are proportional to each other. As long as they have the same number of sides and same measure of angles, then their sides are proportional. It's the fundamental concept in making any kind of scale drawing, whether it's a map, drawing of a house, whatever it is. That's the fundamental concept there. Okay, well that's all for lesson 3.